questions.
Thank you. So there are questions from Rui Chang.
Thank you for a very nice talk. I would like to inquire about the predictive power of this result. Like, for instance, can we verify your results, for instance, using some existing experimental data? My concern is on this, for instance, on this Bmax, which is hard to measure, I think.
I mean, of course, if we know the model, it can we can verify our band, and then yes, if we want how the transition rates respond to the model, we can verify our result, because of course it is exact identity, and then verification just corresponds to checking whether the analyzed system is correctly described by the Markov model with which we simulate that, because it is an exact identity. And in some particular models, we can determine all transition rates and how they depend on control parameters, because, for example, in quantum dot systems, we can really solve between all transition between different states of the system, and also how these rates react to the applied parameters. So in this sense, we can, in that sense, we can verify that. But of course, Bmax, the system is problematic in our band because it is model dependent. But our primary motivation, even though we are discuss some applications, was really to give some mathematical form to our intuition that the responses, that there must be some thermodynamic cost of response to those kinetic perturbations. And this was our original motivation, which was quite more fundamental than practical. And later our study produced this and this new identities. But I think the whole potential, whole applicability of these identities is not full understood how they can be applied later in practice. But for example, in the second paper, actually, we also discuss a bit how our identities can be actually, for example, used to calculate fluctuations for some models for which we can determine exactly the steady state. And then we can, for example, calculate fluctuations analytically, which is not possible for using different methods. It is another way to apply our result, I believe.
Yeah, thank you. My biggest concern is on the form of this response. I'm also doing something on this kind of system. So this perturbation on a single transition rate, or for instance, can that correspond to some practical experiment in real world system? Like,
Yeah. For example, by controlling anti voltages in quantum dot system, they usually affect only tunneling rates in the model, but they don't affect the thermodynamic forces acting on electrons. So one can really realize such perturbations, which with good approximation affect only kinetic barriers, but not thermodynamic forces.
okay, thank you very much.
So the next question is from Thomas.
Thank you for the talk, Christoph. So you said that there was like a thermodynamic bound on the TUR that you get for current perturbations. You said there was a minimal thermodynamic cost. Do I understand that you're saying there's a minimal sort of housekeeping entropy production of the underlying system in order for you to induce a certain change? Or is it also a function of the sort of change, the perturbation that you're applying? Like how much the perturbation costs?
Of course, this band shows that there's some minimum this housekeeping entropy production cost, but also it depends actually in the model, because if also the transition rates depends strongly, very strongly on the control parameter, then we can have a strong response with a small entropy production rate. But usually the response of this transition rates to this control parameter are some constrained by the laws of physics. And then if the value of this response of transition rates is somewhat bounded, then to increase the response, we must also increase the thermodynamic cost.
Okay, thank you.
Yes, the last question is from Luke.
Hello, can you hear me?
Yeah.
Yes,
hi.
yes.
Thank you for the very nice talk. What is the biggest challenge in so the reservoirs are thermal. If you have reservoirs that are maintaining a non-equilibrium steady state.
Yeah, I mean, this formalis, we use always set formalis of stochastic thermodynamics, and is derived from the assumption that reservoirs are in equilibrium. So I don't have a very easy answer to your question. Probably there are some generalization of this formalis to non-equilibrium reservoirs using some super reservoirs, for example, which are at equilibrium, but I have no intuition about that.
And just another follow-up question. So the control parameters are in, I guess the difference in energy levels is BE. If you're controlling sort of the currents, the edge currents themselves, so if epsilon is in SE over 2, yeah, that's also quite interesting, but also very challenging, right?
Yeah, you mentioned energy levels. Usually, energy levels in the system will affect both these parameters B and S. So it is quite problematic, but we can find sometimes such perturbations, especially we can find the kinetic perturbations which affect only B's and but not SS. But it's not usually not through modulation of let us say energy levels of the system, but rather by modulating in some way the strength of interaction with different reservoirs, which can be realized in practice in different models.
Okay, so it's time now. So yes, thank you, Christoph, for a very nice talk.
Okay, thank you
So
very
we
much.
move to the last talk of today. So next speaker is Dominik Hahn. Dominik, can you share the screen?
Yeah. Do you see it?
Okay.
Do you see my slides?
Yeah. Okay, perfect. Yes, please go ahead.
Okay. Yeah. Thanks a lot for the invitation. Today I want to talk about the quantum many-body Jarzynski equality and dissipative noise in a digital quantum computer. This is work I have done with my collaborator, Maxime, Markus, David, and Marin, and this is published in PRX. To motivate this, I want to study non-equilibrium work fluctuations. And to be more concrete, when you consider nanoscale thermodynamics, then work fluctuations become important. To illustrate this, consider a piston. When you compress it, you perform some work. So you begin in equilibrium, change the system from A to B, and the average work you get out of it is due to the second law of thermodynamics, larger than the free energy difference. And but it turns out when you are working at the nanoscale, then the work you can extract among multiple repetitions is not sharply peaked, but you have a distribution. And in fact, you can strengthen the second law of the inequality of the second law of thermodynamics and basically get the equality when you consider the averaged exponential work distribution and compare it with the free exponential free energy difference. And this is the celebrated Jarzynski equality. of course, we want to extend it to quantum mechanics, but this is not straightforward because work is not observable. So in order to overcome this issue, it turns out that you can define work in quantum mechanics as a two-point measurements. W is equal EF minus EI. And what I mean with it is basically that you measure at the beginning, you collapse the state to an energy eigenstate, initial energy eigenstate, perform a protocol, and do the end also for the in the final Hamiltonian. And when you do this, you obtain a quantum version of the Jarzynski equality, and you can in principle realize it experimentally, which has been done for single qubits or trapped ions. Before I proceed about our contribution, I want to show a quick proof of the quantum Jarzynski equality. The idea is when you consider the exponential work difference, with, which is given by this object, you basically have an initial weight, you have a transition matrix between initial and final energy, and then this is the weight for each exponential work. With some standard manipulations, you can simplify it. You need here a sum rule, to which I will come later, but from this you directly obtain quantum Jarzynski equality. So the only ingredient which flows into the derivation is the sum rule, and this is known as double stochasticity. So which is generally known as when you sum over n. This is related to probability conservation, and this double stochasticity is fulfilled for unitary dynamics and also when you have dephasing, but not for systems with dissipation. And this basically means that we can use this quantum Jarzynski equality as a test of dissipation. Okay, now, as I mentioned before, it has been the quantum Jarzynski's equality has been studied for single particle physics. So our motivation was to extend it to many-body quantum systems. One thing is is what I mentioned before, is to quantify dissipation. Then it's also testing fundamental laws of microscopic processes on a more mesoscopic level and see whether you can see deviations, and also to extend basically this gap. As I shown here, this were all the previous experiments before we worked on this, and these were limited to at most 3 qubits. However, this is not straightforward. So you need, in order to do this, you need control of many-body quantum systems. You have to figure out how to measure work in a many-body system, and also how to prepare thermal ensembles. And what you also need is to get probability distributions. You need an extensive number of measurements. It turns out the perfect solutions to tackle all these problems are digital quantum computers, which are basically many-body quantum systems in itself. Furthermore, it allows, because of flexible access to quantum gates, flexible preparation of non-equilibrium protocols, and you can have full access to all degrees of freedom via measurements. And it can be, of course, also simulated multiple times. Which we will also do is that we will realize it on different platforms, namely trapped ion platforms and superconducting qubits, and see a comparison of these two machines. Our idea is basically what we will do is we start with we fix an initial and a final Hamiltonian. The initial Hamiltonian will be the transverse field IC model. The final will be a Z model. Compute classically the free energy difference. And on a quantum computer, we can simulate this protocol, perform a non-equilibrium process, and including noise of the quantum computer, and then extract the work during this process, and then we will check whether this equality is fulfilled with these properties. Coming back to these challenges, this control of many-body quantum systems is trivially fulfilled. The measurement of works is also good by using Hamiltonians equivalent to free fermions. In this case, you can map your Hamiltonians to a diagonal Hamiltonian in a computational basis with a logarithmic circuit, and then you can access to the initial and the final energy. And for preparing thermal ensembles, it turns out when you have for a single particle Hamiltonian, you can basically start from single qubits in a ground state, applying unitary such that you are in superposition with weights given by the canonical ensemble. And when you perform a measurements afterwards, you are in a mixed state, which is given by the thermal ensemble. And also, finally, the extensive number of measurements is also doable on quantum computers. Our idea is basically first prepare these thermal states with mid-circuits measurements, and this we can also use to measure the initial energy. In cases where these mid-circuits measurements are not available, you can replace these mid-circuit measurements by classical pre-sampling. Afterwards, you can transform in the spin eigenbasis of the transverse field eigenbasis with a shallowed circuit, which only needs so-called Bourgoulio-Boff gates and Fourier transform gates and Megonnier swap gates. And then we can apply an arbitrary non-equilibrium protocol. In the previous experiments, they often use parametric ramps. We use a completely random circuits, and then finally measure. Okay, as a first test, we considered different platforms, and what we basically plot is the logarithm of the exponential between the vector difference and the free energy difference. In the ideal case, it should be equal to 0. Everything which is away from 0, it can be attributed to errors or statistical fluctuations. In our first case, we considered small systems with 4 qubits and used classical pre-sampling for thermal state preparations. The reason was that on not all platforms mid-circuits measurements are available. So basically, when you compare it, you can first consider 2 superconducting quantum computers. What you see overall is a linear growth in with the inverse temperature, and you see also that you see basically that you are not strictly at 0, but you have deviations which are beyond statistical uncertainties. When you compare it with trapped ions, you see that they also perform strictly better in comparison to superconducting circuits. However, it turns out that for practical reasons, simulations on trapped ion devices is more expensive. This is basically because the execution times of circuits on trapped ions takes longer. And so for scaling up, we use the IBM quantum computers instead. To do so, we tested it on IBM Guadalupe for up to 60 qubits. You can see here the results. What you see is that the absolute error grows linear with system size and inverse temperature. In order to get a better understanding what happens, we normalized it in some sense with the maximal possible deviation, which is basically the case where, when you, instead of getting the final measurements, you always relax to the ground state. This is the worst case you can happen, and we normalize the error by the worst case. And what happens then is that the normalized error shows only a weak dependence on system size and temperature, which is quite good. Now, I mean, you see here some absolute values, but it's hard to make any statements how good these results are. So we considered a comparison with a pure dissipative process. So instead of doing this non-equilibrium protocol, we apply gates at all, and just wait for the same time the execution of the quantum circuit takes. So what you can see here are the results for 8 qubits as a function of the idle time in comparison to this relaxation time of the single qubit gates. And basically what you can see is that, as you would expect, the error increases when you wait longer. However, what is remarkable is that when you consider the deviation of our protocol, including quantum circuits, which is shown as a diamond here, then you see that these deviations are 1 order of magnitude smaller than a pure dissipative process. So basically the random gates, they improve this result. In order to understand this, you can look at these random gates, and what happens is they serve as a drive which compensates for dissipation. So basically, your excited state population decays, but it's repopulated by these quantum gates. And when you do it repeatedly, I mean, you are not perfect, but you have at least an improvement to the pure idle time of the circuit. So to sum up, basically we discovered an emergent new regime where the quantum Jarzynski equality holds, even if you have a strong dissipation. This has not been explored before. Before it was known it works in a unital case only. And also when you compare it with our previous results, we basically scale up the system size by 1 order of magnitude, and also the relative accuracy. When you compare it with other experiments and measure it here, is roughly the same order as you have seen in the other experiments. To conclude, we have shown the first test of the Jarzynski equality, the many-body regime. We discovered a new emergent regime where the quantum Jarzynski equality holds in the presence of dissipation. And for the future, you can think whether you can use the quantum Jarzynski equality as a new benchmark for quantum devices. So this is in fact basically very close to the standard measurement for the relaxation times. In this case, you excite a single qubit and wait a measure, which is basically the special case with 1 qubit of our idle process. And finally, you can ask whether you can use this the quantum Jarzynski equality in a many-body regime also to measure free energy differences. Thank you for your attention, and feel free to ask any questions.